And start sharing the screen. Okay, so we're over here. I'm going to lecture on 11.2 a while. Okay, I don't know how far I'll get, but we'll see. And then coverage-wise, so here we are. So on the original schedule, it was 11.1, exam 4, we're on 11.2. So next Thursday, of course, this doesn't make any sense. So Thursday, it'll probably be 11.2, 11.3, something like that. We'll see how it goes. Okay, again, I'm trying to make up a day to avoid having to give you the last test on the 15th of December. Okay. All right, so I'm going to go straight to section 2. Okay, the topic is series. Okay, so here's 11.2 series. Okay, so what's the difference between a sequence and a series? So sequence, we had A1, A2, A3, and so on last time. For series, we're adding up all the terms, A1 plus A2 plus A3, and so on. Okay, almost all the rest of this chapter is going to be series. So only section 1 was on sequences. Now we're more interested in series. Okay, we're adding things up. Okay, and also want you to be familiar with this summation notation. This is the Greek letter sigma, a capital sigma, n equals 1 to infinity of a sub n. Or we can just simply write summation of a sub n. Okay, we're almost always going to consider infinite series. Okay, so we don't have to bother writing infinity. And normally we start at n equals 1, although we don't have to. We could start at n equals 0. Sometimes we're going to start at n equals 0. In fact, further on down the line, we're going to start almost all of our series at n equals 0. Sometimes you can't start at 1 because plugging in 1 isn't allowed for some reason. Then you might have to start at n equals 2 or n equals 3. But for the most part, we're going to start at n equals 1. Okay, so for series, you're adding up all the terms. Okay, so most of the time, we're going to consider series. Okay, one special series is something called a geometric series. In a geometric series, every term is multiplied by a common ratio that we call r in order to get the next term. So you keep multiplying by the same thing. Okay, so this is an example of something which is not geometric. 1 plus 2 plus 3 plus 4 plus 5. That's not geometric. You don't keep multiplying by the same thing. Okay, now temporarily ignore all the red. I'm kind of giving away the answers here, but maybe I should cover it up. Okay, 1/2 plus 1/4 plus 1/8 plus 1/16. That's considered geometric with a common ratio of 1/2. Okay, so after the first term, 1/2, you keep multiplying by 1/2. So 1/2 of 1/2 is 1/4. Multiply that by half, get that. Multiply that by half, you get that, and so on. Okay, and you keep adding infinitely many terms. Okay, here's one: 7 plus 21 plus 63 plus 189. The common ratio is 3 for this geometric series. Okay. 1 minus 3 plus 9 minus 27, okay, the common ratio is -3. Okay? And as you can probably guess, if the common ratio is a negative number, then the series will alternate, plus, minus, and so on, right? Okay, 8 plus 0.8 plus 0.08 plus 0.008, okay, the common ratio is 0.1, or you can say 1/10. Okay, 1/10 of that is that, 1/10 of that is that, 1/10 of that, and so on. Okay, how about 2/3 minus 4/9 plus 8 over 27 minus 16 over 81? So it's alternating. So it's alternating. It's a giveaway that the r is a negative. And in this case, it's a -2/3, right? So starting from 2/3, if you keep multiplying by -2/3, you get the next term. Okay, and the dot, dot, dot means we never stop. These are infinitely many sequences. It just, or series. It keeps going on and on and on. Okay, so these are geometric series. Of course, not every series is geometric. Here's a series which is not geometric. There's lots of other series. Well, the very fact that we have, what, 11 sections in this chapter, that itself should tell you not every series is geometric. We've got lots of other stuff to learn. Okay, 2 plus 2 plus 2, blah, 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 blah. Okay, that's geometric where the common ratio is 1, right? 2 minus 2 plus 2 minus 2, the common ratio is -1. Okay, here's one: 7 plus 0 plus 0 plus 0. Okay, common ratio is 0. So that's okay. Then 1 plus 1/2 plus 1/3 plus 1/4. that is not geometric. Okay, there's an obvious pattern to it. In fact, we're going to study this shortly, maybe even today, but this is not geometric. Right? You don't keep multiplying by the same thing. Okay, so if you go from 1 to 1/2, you multiply by half, right? But to go from 1/2 to 1/3, that's not a half, right? Half times a half is 1/4. So this automatically tells me it's not geometric. Okay, now I already gave the answers away here in red, but let me cover it back up. Suppose I were to ask you, which one of these do you think will converge to a real number, and which ones will not converge, which means they diverge? Okay, let's look only at the geometric ones. Well, we could look at this one. 1 plus 2 plus 3 plus 4, that does not converge. It looks like it blows up to infinity, right? That clearly just gets as big as you want. Okay. How about this one? Half plus 1/4 plus 1/8. Okay. It looks like you're adding smaller and smaller and smaller terms, right? So it looks like maybe it converges to some number. This one blows up, gets bigger and bigger and bigger. This one, it does alternate, but the absolute value of the terms get bigger and bigger, right? So this looks like it shouldn't approach anything, right? So we think this one would diverge. This one looks like it might converge. In fact, this one's pretty easy to tell what it converges to. What does it converge to? It converges to 8.88888888, right? This just tells you add the next 8, add the next digit. So we know what this converges to, 8.8888. Okay, how about this one? It alternates, but the terms look like they're getting smaller as the sequence goes farther and farther out, right? So since we're adding smaller and smaller terms, it looks like it might converge. This one blows up, right? It gets as big as you want. If you just add infinitely many 2's, right? The dot, dot, dot does mean infinitely far. Okay, this one's a little tricky. 2 minus 2 plus 2 minus 2. Do we approach any one number? Okay, so if you look at the sequence of partial sums, as it's called, okay, so go partial sums. So 2, 0, 2, 0, right? The sequence of partial sums, if I just add up as I go along, right? So the sum is 2, now the sum is 0, now the sum is 2, now the sum is 0. So it bounces back and forth between 2 and 0. So do we approach a number, any one number? The answer is no. So this series diverges. How about this one? 7 plus nothing plus nothing. Okay, that definitely converges. And you know what it converges to. Doesn't matter how many zeros I add, it converges to 7. Right? So which one of these seem to converge and which ones diverge and why? Well, I've shown you now what our guess was. Converge, diverge, diverge, converge. Okay, so what seems to be a characteristic for the convergent cases? R is a half, 1/10, negative 2/3, 0. How about diverges? R is 3, negative 3, 1, negative 1. Okay, so when we multiply by a number between negative 1 and 1, that makes the number smaller in absolute value, right? And that happens to be the case. Okay, now there's a derivation here, okay, because, under the COVID pandemic, I'm cutting back on what I'm supposed to go over. But if you want to see a derivation of the formula, here it is. So I'm just showing it to you. You can look at it or not, okay? But there's a formula for the sum of a geometric series. So there's a derivation. If you say, I don't understand it, that's okay. I'm not holding you responsible for it anyway. But there it is. Okay. For a finite geometric series, this is a sum. Okay. And now if you let n approach infinity, okay, if r is between negative 1 and 1, like 2/3 or negative 2/3, okay, then r to the n approaches 0. If this approaches 0, just forget about it. You have a times 1 or a over 1 minus r. Okay. So for your next cheat sheet, not for today's test, but for test 5, for a geometric series, if the absolute value of r is less than 1, Another way of saying it is that R is between -1 and 1. Then the infinite sum is A over 1 minus R, where A is the first term and R is the common ratio. Only use this formula if R is between -1 and 1. If R is not between -1 and 1, you're going to get a real number, but it doesn't represent anything. Okay, example. This one we did here. 1 plus 2 plus 4 plus 8. Well, I thought I did it, but I guess not. Okay, you know that blows up. Gets as big as you want. R is 2. You could plug into the formula. There's nothing stopping you. A over 1 minus R, the first term is 1. The common ratio is 2. 1 divided by 1 minus 2 is -1. You say, oh, this infinite sum is -1. That's nonsense. You know it isn't. Okay, so what was faulty? The faulty thing was you plugged into the formula, which is only valid if R is between -1 and 1. Okay, so again, how do you prove it? By all this. Okay, I'm just showing it to you. I'm not going to go over it. I'm not holding you responsible for it, but if you want to look at it, it's there. The book also goes over this. Okay, how about this one though? 1/2 plus 1/4 plus 1/8 and so on. Okay, the common ratio is 1/2, so this one should converge. What does it converge to? The formula is A over 1 minus R. What's A? The first term. R is the common ratio. Okay, so the first term is 1/2 over 1 minus R, which is also 1/2. So 1/2 divided by 1/2, so 1. This series converges to 1 is the language that we will say. Okay. And if you look at the partial sums, okay, in other words, look at the sums as we go along. Okay. So 1/2, this is 3/4, right? 3/4 is the same as 6/8. Plus 1/8, this is 7/8. Okay. The next one will be 1/16. If I add that, it would be 15 over 16. We get really, really, really close to 1. We get as close to 1 as you want. Okay, we never pass 1, but we get as close as you wish. Okay, so we say the infinite sum is 1. Let's look at this one where I said it was 8.888888. Okay, the common ratio is 0.1, so it should converge. The formula is A over 1 minus R. So A is the first term, 8 over 1 minus 0.1. That's 8 over 0.9, or 80 over 9, or 8 and 8/9. Okay, so it converges to 8 and 8/9. Let me just for fun show you 80 divided by 9, and there we go, 8.88888. If you look at it, you say, oh, of course, right? That's 8 plus 0.8 plus 0.08 plus 00. You're just getting the next digit, so that's 8 and 8/9. Okay. How about this one? 2/3 minus 4/9, and so on. The common ratio is -2/3, so that means it should converge. Okay, so the sum is A over 1 minus R. A is the first term, 2/3 over 1 minus the common ratio, which is -2/3. That's 2/3 divided by 5/3. Okay, and I think I've shown you the shortcut before. You can just cancel the 3's, so 2/5. Okay, so I'll start doing some of the homework problems. 11.2. Okay, so problem 19. So does it converge or does it diverge? Again, these problems may not match yours, but that's okay. You're still learning the material, hopefully. Okay, so does a series converge or diverge? And if it converges, what does it converge to? So 10 minus 2 plus 0.4 minus 0.008. So the common ratio is -1/5. By the way, if you can't figure that out, you can always just take the second number and divide it by the first number, right? -2 divided by 10 is -1/5. Okay, is that between -1 and 1? Yes, it is. So the series converges. So let's say this came out to be -5. The series diverges. Don't use the formula. So S is A over 1 minus R. So A represents the first term, 10 over 1 minus a minus 1/5, 1 minus R. So that's 10 divided by 6/5, which is 10 times 5 over 6. And after canceling, you get 25 over 3, 8 and 1/3. Okay, so the series converges to 8 and 1/3. problem's finished, but I'll dig a little deeper. Let's look at the partial sums. 10 minus 2 is 8. 8.4. It's already pretty close, right? 8.4 minus, that's 8.32. This is 8.333 repeating. So even after 4 terms, it does seem reasonable that we're converging to 8 1/3. Okay, my 23 looks like this. Summation is n equals 1 to infinity of -3 to the n minus 1 over 4 to the n. Now get used to this notation, the summation notation. Okay, and I think the best thing to do is just plug in some numbers. Okay, so what do you get when you plug in 1? -3 to the 0 is 1. 4 to the 1 is 4. So 1/4. Plug in 2. -2 minus 1 is -3 to the 1. So -3 over 4 squared is 16. So -3/16. Plug in 3. -3 squared is 9. 4 cubed is 64. Plug in 4. -3 cubed is -27. 4 to the 4th is 256. Okay, so you see the pattern. So how do you go from here to here or here to here and so on? You multiply by -3/4. Right? So 1/4 times -3/4 is -3/16. -3/16 times -3/4 is 9/64 and so on. Okay, trade secret. Quite often, okay, this is not foolproof, but quite often you can find a common ratio if you just look over here, -3/4. Okay, it's not absolutely correct, but for me, when I look at this, I would highly suspect, I guess is the way to say it, I suspect the common ratio is -3/4, but you want to double check for that. Okay, is that between -1 and 1? Yes, it is. So the series should converge. Okay, so the formula is A over 1 minus R. So A is the first term. So use 1/4. Don't use -3/16 or anything else. So 1/4 over 1 minus R, 1 minus a -3/4. 1/4 divided by 7/4, drop the 4s, 1/7. Okay. All right, 25. Summation n equals 0 to infinity of pi to the n over 3 to the n plus 1. Okay, so I plug in 0. Notice this time they're starting at 0. That's allowed. Okay, so plug in 0. Pi to the 0 is 1. 3 to the 1 is 3. So 1/3. Plug in 1. Pi to the 1 over 3 squared is 9. Plug in 2. Pi squared over 3 cubed is 27. Okay, and you can see, and this is what we suspected. So our guess is multiplied by pi over 3. So 1/3 multiplied by pi over 3, you get that. Multiply that by pi over 3, you get that, and so on. So the common ratio is pi over 3. That's bigger than 1. This is 3.14, blah, 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 divided by 3. Greater than 1, so the series diverges. So do not plug into the formula, right? R has to be between -1 and 1. So that particular series diverges. Okay. All right, so that's some geometric series that we have. Okay, so a little bit more that I want to show you. Okay, so again, for a geometric series, and there are a lot of series which are not geometric. Okay, we're only on 11.2. We have to go to 11.11. There's a lot of other series out there. Okay, so what's a series? You're adding up the terms of a sequence. Okay, if R is between -1 and 1, the series converges. And my abbreviation, sometimes if the context is clear and we know what we're talking about, I'll put SC for series converges. And the series sum is A over 1 minus R. Sometimes we put A1. Last time we did A1 for the first term. Okay. If the absolute value of R is greater than or equal to 1, which means R is 1 or bigger, or -1 or smaller, the series diverges. And my abbreviation is SD for series diverges. Okay, now the book goes over a theorem. Okay. And here's my abbreviation. If a series converges, SC, series converges, A sub n approaches 0. The individual terms have to approach 0 if a series converges. Okay. Let's see where that is in the text. Yeah, page 713. If a series is convergent, limit as n approaches infinity of A sub n equals 0, or A sub n approaches 0. Okay, so if you know the series converges, A sub n has to approach 0. Okay, so that's what I mean by my shortcut abbreviation there. Okay, if the series converges, A sub n approaches 0. Okay, the logical contrapositive. Okay, that's a logic term. Okay, what is contrapositive? You turn these two around and say not. Okay, the logical contrapositive is always equivalent to the original statement. Okay, so if I change around the if and then and put not, okay, it would say A sub n does not approach 0, then the series diverges. Okay, so if A sub n does not approach 0, so X meaning not, no left turn, no smoking or whatever, right? If A sub n does not approach 0, the series diverges. Okay, so that's called the test for divergence. I will abbreviate TFD. If A sub n does not approach 0, the series diverges automatically. Okay, so that's called the test for divergence, abbreviation TFD. Bottom of 713. Test for divergence. If the limit as n approaches infinity of A sub n does not exist, or if the limit as n approaches infinity of A sub n is not 0, the series is divergent. Okay, so again, my abbreviation, A sub n does not approach 0. That could mean it approaches another number, or it approaches infinity or negative infinity, or doesn't approach anything. Then the series diverges. Okay, that's called the test for divergence. I'll have a lot of abbreviations. Okay, that's TFD. Okay. And here's an example. My 29, summation n equals 1 to infinity of n minus 1 over 3n minus 1. Okay, does it converge or does it diverge? Okay, the limit as n approaches infinity of n minus 1 over 3n minus 1 is clearly 1/3. Okay. Several arguments. You can say when n gets super big, ignore the minus 1, right? So it's essentially n over 3n, which is 1/3. If you plug in a million, you have a million minus 1, that's basically a million. 3 million subtract 1, that's 3 million, right? If someone has $3 million, they're not going to sweat it. They shouldn't sweat it if they lose $1. Right? They still basically have $3 million. Okay, it's equal to 1/3. You could also do this by the trick in Calc 1. You could divide top and bottom by n. Okay? Or you could also do L'Hopital's rule. Remember, L'Hopital's rule, take the derivative of top 1, derivative of bottom is 3. Okay, the terms approach 1/3. Okay, therefore, this is our abbreviation for therefore, ... Therefore, the series diverges by the test for divergence. Test for divergence. Okay, when this goes farther and farther and farther out, when n gets bigger and bigger and bigger, it looks more and more like 1/3 plus 1/3 plus 1/3 plus 1/3 plus 1/3 infinitely many times. And if you add up infinitely many 1/3s, that blows up, right? Okay, so we're going to say the series diverges by the test for divergence. Okay, so if the series converges, A sub n approaches 0. Okay, is the converse true though? In other words, if I just switch around the if and the then, if A sub n approaches 0, does that automatically mean the series converges? Right? So right now we have it one direction. The series converges. Then we know A sub n approaches 0. How about the other way around? If the A sub n's, the terms approach 0, does the series automatically converge? Or another way of saying it is it possible for the individual terms to approach 0, but the series does not converge? Right? So that's the question, and I'll leave you hanging right now. So I was going to stop right there. So I'll answer that question next time on Thursday, but that's as much as I was going to discuss right now. Okay, so let me stop this right here, and let me see if you have any questions about anything. And I will check the chat. If anybody has something here. All right, I don't see anything there. Okay, so you may ask questions all the way up until a maximum of 8:25, because I'm promising you 50 minutes, but if you want to start earlier, that's okay by me. Okay, so let me get
I have
ready and see if anybody has any questions. Okay, so go ahead and put it in the chat, or you can unmute yourselves.
I have a
If
few.
you have anything, we can just go ahead and start. So yeah, go ahead.
10.243 and 10.4 29 and 39.
10.243.
Yes.
And also 10.4
39 and 29.
39, 29. Okay.
Yeah.
10.363. I see. Okay. And anybody else? Again, I can't see the chat and share screen at the same time, so it's one or the other. So I'll have to keep bouncing back and forth, but of course that wastes a little bit of time. Okay, I don't see anything else there. Okay, so you can go ahead and put something in the chat, but I won't be able to see it while I go back and share the screen. Okay, so let me see what we got. 10.243. Find the exact length of the curve. Okay, so x equals t sine of t. Y is equal to t cosine of t. T between 0 and 1. Okay, so I'm doing arc length as the integral from a to b of square root of dx dt squared plus dy dt squared dt. So dx dt is equal to first times the derivative of the second plus second times the derivative of the first. Dy dt, first times the derivative of the second plus second times the derivative of the first. Oops, that shouldn't have a t there. And this should be cosine t. T cosine t plus sine t, yes. T times negative sine t plus cosine t, right. Okay, so the arc length is the integral from 0 to 1 of square root of t cosine t plus sine t squared plus negative t sine t plus cosine t squared dt. Okay, so t squared cosine squared t plus 2t cosine t sine t plus sine squared t. And I think I'm going to scroll down, so to speak, plus t squared sine squared t minus 2t cosine t sine t plus cosine squared t dt. These cancel out. This is t squared plus 1. T squared cosine squared plus t squared sine squared. If you factor out, you have t squared times cosine squared plus sine squared, so that's t squared, and this is 1 dt. Okay, so that's going to require a substitution, right? So t equals tan theta dt equals secant squared theta d theta. And t equals 0, theta equals 0, t equals 1, tangent of pi over 4 is 1, theta equals pi over 4. So the I becomes integral from 0 to pi over 4 of radical, okay, tangent squared theta plus 1, dt is secant squared theta d theta. 1 plus tangent squared is secant squared, so that gives me a secant cubed. Okay. So this is secant theta. So integral from 0 to pi over 4 of secant cubed theta d theta. Okay, this is going to take quite a while for me to finish, so I think I'm going to have to stop and say etc. You would break it into secant squared and secant, and you have a choice then of either integrating by parts or substituting. Okay, so secant squared theta and secant theta and so on. Okay, so sorry, in order to save time, I'm going to have to abandon the problem, but that would be the setup, and we've tackled that kind of problem before. Okay, 10.363. Okay, I'm not sure how much I want to do with that because I think I did that before. R equals 1 plus cosine theta. Yeah, I'm afraid I'm going to have to say we did that. Okay, so look back in your notes for that. Okay, did before. That one did have some issues for vertical and horizontal tangents. Remember, to have a vertical tangent, the denominator is 0 while the numerator is non-zero. And for horizontal tangent, the other way around, the top is 0, but the bottom isn't. Okay, and it's going to take me too long, unfortunately, to go over that. So we did it. Look back in your notes. I'm pretty sure we covered that earlier. 10.4, 39, and 29. R equals 2 sine 2 theta, and R equals 1. Okay, so find points of intersection. Okay, ordinarily we'd have to check the pole, but in this particular case, you don't have to worry about that. Okay, so this can never touch the pole. So I just set them equal. 2 sine 2 theta equals 1. And this gets a little tricky. 2 sine 2 theta equals negative 1. If I take R equals 1, it looks like that, but R equals negative 1 also looks like that. Okay, so I have to do both of these. Okay, so sine of 2 theta equals a half, or sine of 2 theta equals negative a half. Okay, so unit circle. Y coordinate is a half or negative half. That's there, 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 and there. So this is pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. So two theta is pi over 6 plus 2k pi, or 5 pi over 6 plus 2k pi, or 7 pi over 6 plus 2k pi, or 11 pi over 6 plus 2k pi. Okay, that's 2 theta. So if I multiply through by 1/2, I cut that in half, I cut that in half, cut that in half, cut that in half. So theta is pi over 12 plus k pi. Or let's see, that's 5 pi over 6. So 5 pi over 12 plus k pi. 7 pi over 12 plus k pi. And 11 pi over 12 plus k pi. Okay, now if I take multiples of pi, okay, we already know it has to be in r equals 1. So my x-coordinate is 1. I just basically keep going around the circle. So pi over 12, 5 pi over 12, 7 pi over 12, 11 pi over 12. Now 11 pi over 12 is like that. And these two guys are like that. So I'm going to have 4 more here if I add multiples of pi. There, 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 and there, it looks like. Okay, so let's see, if I add pi, that would be 13 pi over 12. Okay, I don't have to keep going around the circle because after 2 pi, I just repeat myself. So for theta, I have pi over 12, 5 pi over 12, 7 pi over 12, 11 pi over 12. Okay, now if I keep adding multiples of pi, so that gives me 13 pi over 12, and let's see, 17 pi over 12, and let's see, 19 pi over 12, and 23 pi over 12. Okay, so all the r coordinates are 1. So 1 comma, 1 comma, 1 comma, 1 comma. Sorry, this is going to be a while. 1 comma, 1 comma, 1 comma. And these 8 numbers all go here, if you don't mind. So pi over 12, 5 pi over 12, they're all pi over 12. So 1, 5, 7, 11, 13, 17, 19, and 23, it looks like. So pi over 12, 5 pi over 12, and so on. Okay, and that'll give me all those coordinates there. Okay, so let's see. That was 10.4, 39, and then 29.
Yes, 29.
9. Inside both curves, r equals 3 sine theta, r equals 3 cosine theta. Okay, that's very much like my 31 star, only the radius is just bigger. Okay, so they were like this, I believe, if I'm not mistaken. Oh, I'm sorry. Like this. This is my unit circle, as it were. Okay, let me see. Yeah, this is r equals 3 sine theta, r equals 3 cosine theta. See, if I plug in 0 here, I get 3. Plug in 0 here, you get 2. Yeah. Okay, so inside both curves was this part. This was pi over 4. Okay, so if we were to draw it more accurately, but you don't have to, you just find the points of intersection, go like that. But r 3 cosine theta looks like that. 3 sine theta looks like that. Okay, so if I just go from 0 to pi over 4 and double it, I believe I have what I need. And if I'm integrating on this one, that's this one here. Okay, so the area is twice integral from 0 to pi over 4 of 1/2 r squared. In this case, it's 3 sine theta squared d theta. Okay, because if I cut like that, by symmetry, this matches this. So to make it easier, I'll just go from 0 to pi over 4 and double it. From 0 to pi over 4, I'm using this one. Okay, and these guys cancel out. So take out the 9, integral from 0 to pi over 4. Sine squared is 1 minus cosine 2 theta over 2 d theta. Bring the 2 out, so that's 9 over 2. Integral of 1 d theta is theta. Integral of negative cosine 2 theta is negative sine 2 theta times 1/2 from 0 to pi over 4. Okay, when I plug in 0, I get 0. 0 minus 0. Plug in pi over 4. Pi over 4 minus, if you plug in pi over 4, I'm taking the sine of pi over 2, which is 1. So it's like that. So 9 over 2 times, let's see, times 2 times 2. So how about pi minus 2 over 8? So 9 over 16 times pi minus 2. Looks like that's my answer for that one. Okay. I think I've caught up, so let me check the chat back again. Let's see. Somehow I lost stuff in the chat. 10.3. Yeah, 10.360, that was the one that I wasn't going to do. Okay, I think I've caught up. Okay, 7:53-ish. Okay, anybody else, please? If not, then we'll break and take the test. Wait a while. Okay, so we'll break. I have 7:53, so maybe about 8:03, start up again. Sometime in that interval, I will send via Canvas announcements the exam, and then we'll get started, okay? All right, so we'll break. And I'll stop recording also.